Welcome back. Let's practice finding tangential and normal components of acceleration. Alright, so here's our first example. We want to find the general, tangential, and normal components of acceleration for the position vector. And our position vector r of t is equal to ti plus t squared j plus t cubed k. Okay, and so if we want to find the tangential and normal components of acceleration for this position vector, we have to know the formulas. They look like this. At least these are the specific formulas that I recommend that you use for calculating the tangential and normal components of acceleration. There are other formulas for finding these components, which if you want to learn more about those, feel free to check out the lesson video for this topic. But these two right here are what I recommend that you use for most problems where you want to find these two components. A sub t represents the tangential component of acceleration, and a sub n represents the normal component of acceleration. To find the tangential component, we need to take the dot product of the velocity and acceleration vectors and then divide by the magnitude of the velocity vector. For the normal component, we do a very similar calculation, but instead of the dot product between the velocity and acceleration vectors, we take the cross product between those two vectors and then take the magnitude of that vector and divide it by the magnitude of the velocity vector. Okay, so in order to calculate these two components, we need to know the velocity and acceleration vectors as well as the speed or the magnitude of the velocity vector. So let's start with that. Let's find our velocity and acceleration vectors. The velocity vector, v of t, is equal to the derivative of the position vector. So we want to take the derivative of each of these components individually. The derivative of t is 1, so we have just 1i, plus the derivative of t squared, which is 2t, so we have 2tj, plus the derivative of t cubed, which is 3t squared times k. All right, now let's find the second derivative, or the acceleration vector. That will be equal to the derivative of the components for the velocity vector. The derivative of 1 is 0, so there is no x component, but then the derivative of 2t is 2, so we get 2j, and then for the z component, the derivative of 3t squared is 6t. So we have 6t k. All right, multiply that 2 down. 2 times 3 is 6. Subtract 1 from the exponent. 2 minus 1 is 1. So you just have t to the first power. And so now we have both the velocity and acceleration vectors. The only thing we're missing now is the speed or the magnitude of the velocity vector. So let's find that yet. We need to find the magnitude of v of t. So we want to take the square root of the sum of these components squared. 1 squared is 1, so we have 1 plus 2t squared. Squaring 2 gets you 4. T squared is t squared. And then we'll add that to 3t squared. 3 squared is 9, so we have 9. And then t squared squared is t to the power of 4. All right, and so there we have it. That is the speed. We can't really simplify that at all. This expression cannot be factored, and so I'm just going to leave it as it is. So now we have everything we need to calculate these two components, but now we actually have to do the calculations to find them. So starting with the tangential component of acceleration, we need to take the dot product of the velocity and acceleration vectors and then divide by the speed. So we will have a sub t is equal, and let's do the dot product first. We want to take the sum of the product of corresponding components. So we'll start by multiplying the x components. The x component for the velocity vector is 1, but for the acceleration vector it would be 0 because there is no x component. So we have 1 times 0, and then we're adding that to the product of the y components. And so we have 2t times 2. I'll write that down. 2t times 2. And then we have plus the product of the z components. So we have 3t squared times 6t. So writing that down, 3t squared times 6t. Okay, so then in the denominator, we just have to copy the magnitude of the velocity vector, which is the speed. So we have the square root of 1 plus 4t squared plus 9t to the power of 4. All right, and now if we simplify, the tangential component of acceleration will be equal to 1 times 0, which is 0, plus 2t times 2, that will be 4t. So in the numerator, we have 4t plus 3t squared times 6t. 3 times 6 is 18. T squared times t is t cubed. So we have 4t plus 18t cubed. And then the denominator, there's nothing for us to simplify. So I'm just going to rewrite it again. The square root of 1 plus 4t squared plus 9t to the power of 4. And that's it. We really can't simplify any further. I suppose you could pull out a common factor of 2t from these two terms in the numerator, but that's not really going to make a difference for us, so I'm going to leave it as it is. That is a tangential component of acceleration for this position vector. Now let's find the normal component of acceleration. To find that, we need to take the cross product of the velocity and acceleration vectors, and then take the magnitude of that vector. All right, so we're going to have vector v cross vector a, velocity cross acceleration, and that will be equal to the following calculation. You want to set up your 3x3 matrix, and so we'll have I, j, and k. The middle row will have the components of the velocity vector, and the bottom row will have the components of the acceleration vector. For the velocity vector, that is 1, 2t, and 3t squared. So let's write those in. 1, 2t, 3t squared. And then for the acceleration vector, that would be 0 for the x component, and then 2 and 6t. So we have 0, 2, 6t. All right, now calculating the cross product here, let's take this step by step. Start by covering up the I column, calculate a 2 by 2 determinant. 2t times 6t is 12t squared minus 3t squared times 2, which is 6t squared. So for the I term, we have 12t squared minus 6t squared times I. Then we will subtract the j term. So cover up the j column. 1 times 6t is 6t minus 3t squared times 0, but that's just 0. So we're just subtracting 6t times j. Then finally, we'll add the k term, cover up the k column. 1 times 2 is 2, minus 2t times 0, which is 0. So we just get 2k. All right, and then simplifying the x component here, 12t squared minus 6t squared, those are like terms that we can combine. The result will be 6t squared. So this is equal to 6t squared I minus 6tj plus 2k. So that is the cross product of the velocity and acceleration vectors. Now what we need to do in order to find the normal component of acceleration is take the magnitude of that cross product. So we want to take the square root of the sum of the components squared. So here's what that will look like. The magnitude of the cross product between the velocity vector, I'm just going to write it as vector v, and then the acceleration vector is vector a. So the cross product between velocity and acceleration is equal to the square root of 36t to the power 4. Then you want to add that to squaring negative 6t. So we have plus 36t squared. And then you want to add that to 2 squared, which is 4. So we have plus 4. Okay, and so now we're almost done. We can simplify this a little bit, but I'll wait to do that until we put it into this expression for our normal component of acceleration. Let's set that up now. We'll have that the normal component of acceleration, a sub n, is equal to the magnitude of that cross product, this right here, divided by the magnitude of the velocity vector, which is just the speed. So let's write that in here. We have the square root of 36t to the power 4 plus 36t squared plus 4. And then in the denominator, we have the square root of 1 plus 4t squared plus 9t to the power of 4. Now, once again, we can't really simplify the denominator, but in the numerator, there is a common factor of 4 that we could pull out. 36, 36, and 4 are all divisible by 4, and 4 is a perfect square. The square root of 4 is 2, so you could pull that out and just have a 2 on the outside of this expression. And then since everything is underneath the square root, we could just take the square root of the entire fraction. All right, we don't have to have 2 separate square roots. We can combine it into 1. So here's what I mean by that. The way that I will rewrite our normal component of acceleration is like this. We'll have that 2 on the outside times the square root of 9t to the power 4 plus 9t squared plus 1 divided by 1 plus 4t squared plus 9t to the power 4. All right, that is my final answer for the normal component of acceleration. Once again, all I did here was pull out that common factor of 4. Remember that 4 times 9 is 36, so that's why both of those two terms are now 9t to the power 4 and 9t squared. The square root of 4 is 2, so we just pull that 2 to the outside. And then instead of having two square roots, we have the square root of the entire fraction. And there you have it. We have now found both the tangential and normal components of acceleration, at least as general expressions in terms of t. If you wanted to find any specific values for those two components at a specific value of t, you could just plug that value of t into those expressions and find the corresponding value. Okay, let's take a look at another example. Next up, we want to find a tangential and normal components of acceleration for the position vector at t equals 0. And our position vector r of t is equal to e to the power of t times I plus e to the power of negative t times j plus tk. Alright, so this example is a little bit different than our first one. In the first example, we were just looking for the general expressions for the tangential and normal components of acceleration, but this time we're just looking for specific values of those components at t equals 0. So we don't need to find any expressions in terms of t for these two components, we just have to find one specific value for each of them at t equals 0. So that is going to make our work a little bit easier. We don't have to work entirely in terms of t the whole time, and so our work is going to look a little bit different here, but as I said, it's going to be a little bit easier. And so here's what I mean by that. These are the two formulas we used in the previous example. Notice that everything here was in terms of t, but we don't have to do that this time around. We can find the tangential and normal components of acceleration at t equals 0 by just replacing each of the t's in these expressions with 0. What we're going to want to do is find the velocity and acceleration vectors at t equals 0 before we do any of these calculations. Alright, so what we're going to do to find a tangential component is take v of 0 dot a of 0 and divide it by the magnitude of v of 0, or the speed at t equals 0. And then for the normal component, or a sub n, we will take the magnitude of the cross product between v of 0 and a of 0 and divide that by the speed at t equals 0. Okay, so that's our goal here. I'm going to erase these formulas down here now that we have them written up here, but in terms of t equals 0. And so to get started, what we have to do is find the velocity and acceleration vectors and then plug 0 into those vectors. Okay, we have to work in terms of t until we get both of these vectors because you have to have a vector function in terms of t in order to actually take its derivative. Okay, and so starting with the velocity vector, let's find that. V of t will be equal to the derivative of the components of r of t, the position vector. The derivative of e to the power of t is itself, so we have e to the power of t times I, plus the derivative of e to the power of negative t. The derivative of that will also be itself, but you want to be sure to multiply by the derivative of the exponent. Since it's not just t, the derivative of t is 1, so it doesn't matter that we're multiplying by that 1. But in this case, the chain rule does matter. You do want to take that into account because the power of e is not just t, it's negative t, so the derivative would be negative 1. So really, instead of plus the j term, we would have minus e to the power of negative t, because the derivative would be e to the power of negative t times that negative 1. All right, so that's the j term. And then finally, the derivative of t is 1, so we have plus k. Now let's take the derivative again. The acceleration vector, a of t, is equal to the derivative of these components. Once again, the derivative of e to the power of t is itself, so we have the same x component, but then for the y component, we need to take the derivative of e to the power of negative t, so we're going to need to multiply by another negative 1, which will cancel out with this negative, so we have plus e to the power of negative t times j, and then a derivative of 1 is 0, so there is no z component for the acceleration vector. It will be 0. Alright, and so now let's plug in 0 into these two vectors. Starting with the velocity vector, v of 0 will be equal to e to the power of 0 times I minus e to the power of negative 0, j plus k. Alright, now in both of these cases, negative 0 is just the same as 0, right? We don't care about that minus sign. We have e to the power of 0 in both the x and y components. That's just equal to 1. So really what we get here is I minus j plus k. All right, plugging 0 into the velocity vector gives you components of 1, -1, 1. So that's what this right here represents. For the acceleration vector, something very similar will happen. If we plug in 0, we'll have e to the power of 0 for the x component. Once again, e to the power of 0 is 1, so we just get I. And then for the j term, or the y component, e to the power of -0 is just e to the power of 0, which is 1. So we have plus j. Okay, so that's it for the acceleration vector at t equals 0. But now one more thing that we need is the speed, or the magnitude of the velocity vector at t equals 0. So let's take the magnitude of v of 0. I'll do that right here. The magnitude of v of 0 is equal to the square root of the sum of the components squared. So we have 1 squared plus -1 squared plus 1 squared. 1 squared is 1, -1 squared is 1, 1 squared is 1, so you have 1 plus 1 plus 1, which is 3, so you just get the square root of 3 for the speed. Okay? And so now we have everything we need to calculate both the tangential and normal components of acceleration at t equals 0. Let's start with a sub t, the tangential component. Let's take the dot product of the velocity and acceleration vectors at t equals 0. We're going to have 1 times 1 plus -1 times 1 plus 1 times 0. All right, so 1 times 1 plus -1 times 1 plus 1 times 0. And then in the denominator, we have the magnitude of the velocity vector at t equals 0, which is the square root of 3. All right, now in the numerator, 1 times 1 is 1, and then -1 times 1 is -1, and of course 1 times 0 is 0. So this is equal to 1 minus 1 divided by the square root of 3. But if you notice here in the numerator, 1 minus 1 is 0, so really what we have here is 0 divided by the square root of 3, which is 0. 0 divided by anything except 0 is going to be 0. And so what we find here is that the tangential component of acceleration is equal to 0. There is no tangential acceleration at t equals 0 for this position vector. All right, and if you wanted to signify that this is at t equals 0, you could write it like this, a sub t of 0. It might be more appropriate to write it that way in this case. So I'll do that here. But regardless, the tangential component is 0 at t equals 0, which means all of the acceleration is in the normal component. So really, if we wanted to shortcut this, the magnitude of the acceleration vector would all be in the normal component. And so whatever the magnitude is of a of 0 would be the normal component. And so you'd have the square root of 1 squared plus 1 squared, which is the square root of 1 plus 1, which is the square root of 2. So we can already see that that's where this is going, but I am still going to go through the work of doing this cross product just to show you that we still get the right answer. All right, and so let's set up this cross product. Let's actually calculate it here. We're going to take v of 0 cross a of 0. And so setting up that 3 by 3 matrix, I, j, k, the components of the velocity vector are 1, -1, and 1. So we have 1, -1, and 1. And then the components of the acceleration vector, and by the way, both of those, we are looking at them evaluated at 0, not the general vectors, but a of 0 has components of 1, 1, and then 0 for the k term, or the z component. So we have 1, 1, 0. All right, now taking this cross product, cover up the I column, -1 times 0 is 0, -1 times 1. That gives us -1 times I, or just -I. Then we subtract the j term, cover up the j column, 1 times 0 is 0, -1 times 1, which would give us -1. So we're subtracting -1 times j, which means we just have plus j. All right, so plus j, and then plus the z component, or the k term, cover up the k column, 1 times 1 is 1, minus -1 times 1, so we have 1 minus -1 times k. But those two negatives would cancel out, so really we have 1 plus 1, which is 2. And so I'll just erase this and rewrite it as 2k. Now, let's take the magnitude of that vector. We want to take the magnitude of the cross product between v of 0 and a of 0. We're going to take the square root of the sum of those components squared. So we have -1 squared plus 1 squared plus 2 squared. -1 squared is 1, 1 squared is 1, so we have 1 plus 1 plus 2 squared, which is 4. So we have 1 plus 1 plus 4, which is 6. So the magnitude of the cross product is the square root of 6. Now, putting all that together, the normal component of acceleration, evaluated at 0, would be equal to that cross product we just calculated, which is the square root of 6, divided by the magnitude of the velocity vector at t equals 0, which is the square root of 3. So with the square root of 6 divided by the square root of 3, you could rewrite that to be the square root of 6 thirds. Just take the square root of the entire fraction. 6 divided by 3 is 2, and so we do indeed get the square root of 2 as the normal component of acceleration. All right, so I'll just write it like this. A sub n of 0 is equal to the square root of 2. That completes our answer to this example. And that square root of 2 that we just found is exactly what I predicted it would be earlier based on the fact that the tangential component was 0. Remember, the tangential and normal components of acceleration together are telling you how much of the acceleration is pointing in the direction of the unit tangent vector and unit normal vectors. So if none of it is pointing in the direction of the unit tangent, then all of the acceleration is in the direction of the unit normal. And so that would just be the same as the magnitude of the acceleration vector at t equals 0. And you can see that right here, the magnitude of this vector, if you were to take it, would be the square root of 2. So that checks out. All right, but that is it for this example. And so let's move on to another one where we're going to do something a little bit different. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful, then I'd like to invite you to join my membership site, JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. So if you are interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. For this example, we want to find t of t, the unit tangent vector, n of t, the unit normal vector, a sub t, the tangential component of acceleration, and a sub n, the normal component of acceleration, at t equals pi divided by 3 for the given space curve. And our space curve, or position vector, is r of t is equal to cosine ti plus sine tj plus 2tk. Alright, so this problem, as I hinted towards, is a little bit different than what we've done so far. We're still going to be calculating the tangential and normal components of acceleration, but now we also want to find the unit tangent and unit normal vectors. And so since we want to find these two vectors as well, I'm going to make use of some different formulas here. We're going to put to use some of those other formulas that we found in the lesson video for this topic. Specifically, here are the formulas I'm going to focus on. First of all, remember that the acceleration vector is broken up into these two vectors, the tangential component of acceleration times the unit tangent vector, plus the normal component of acceleration times the unit normal vector. That is just our definition of the acceleration vector, but in terms of those two components. But then down here, I have alternative ways for us to calculate the tangential and normal components of acceleration, specifically in a way where we can take advantage of the fact that we also have to find the unit tangent vector. Okay, so before I dive into how we're going to use these formulas and in what order, let's just start by finding the unit tangent vector, since that is something we know how to find pretty quickly. It's just the first derivative of the position vector divided by its magnitude. Or in this case, you could think of it as being equal to the velocity vector divided by its magnitude, right? In the past, I wrote it like this: the unit tangent vector, t of t, is equal to r prime of t divided by its magnitude. So that looked like this. But within the context of velocity and acceleration, it might be helpful to write it like this: the unit tangent would just be equal to v of t divided by the magnitude of v of t. Okay, so let's find the velocity vector. V of t will be equal to the derivative of r of t. So let's take the derivative of each of these components. The derivative of cosine is negative sine, so we have negative sine t I, plus the derivative of sine, which is cosine, so we have cosine t j, and then the derivative of 2t is 2, so we have plus 2k. Alright, so that wasn't too bad. Now what we want to do is find its magnitude, But now I will point out real quick, notice that we aren't just finding the general unit tangent and unit normal vectors, as well as the general components of acceleration. We want to find these four things at a specific value of t equals pi divided by 3. So what I'm going to do before calculating the magnitude of the velocity vector is just plug in that value of t and then take the magnitude, because really what we want to find here is not t of t, but rather t of pi divided by 3, the unit tangent vector at pi divided by 3, since that's the value of t that we were given to work with here. So really what we want to do is take v of pi divided by 3 and divide it by its magnitude. So the magnitude of v of pi divided by 3. All right, so let's plug pi divided by 3 into our velocity vector. We'll have v of pi divided by 3 is equal to negative sine of pi divided by 3. Sine of pi divided by 3 is the square root of 3 divided by 2, but don't forget about that negative. So we have negative square root of 3 divided by 2, and that's multiplied by I. And then we have plus cosine of pi divided by 3, which is 1/2. So we have plus 1/2 j, and then plus 2k. There's no t's there, so we don't have to plug anything in. Okay, so now let's take the magnitude of this vector. The magnitude of v of pi divided by 3 is equal to the square root of each of these components squared. Squaring the negative square root of 3 divided by 2 will remove that negative. The square root of 3 squared is 3, and 2 squared is 4, so we get 3/4 plus 1/2 squared, which would give us 1/4, and then plus 2 squared, which is 4. But then 3/4 plus 1/4 is 4/4, or 1. So you have 1 plus 4, which is 5. So the magnitude here is just the square root of 5. Okay, and so now we can find the unit tangent vector at pi divided by 3. We'll take this vector and divide it by this magnitude. And so here's what that will look like. We'll have t of pi divided by 3 is equal to this vector divided by this magnitude. So I'll just write it as 1 divided by that magnitude of the square root of 5 times that vector. So we have the negative square root of 3 divided by 2 times I plus 1/2 j plus 2k. All right, and so that is the first answer that we're looking for in this problem. We found the unit tangent vector. We didn't really do anything new yet in this problem. We're going to get to using these formulas in just a second. In fact, almost immediately, because where I'm going to go with this is notice that we can find the tangential component of acceleration by taking the dot product of the acceleration vector with the unit tangent vector. And we have the unit tangent vector at pi divided by 3, so what we want to do is find the acceleration vector at pi divided by 3, and then we can take the dot product to find a sub t. All right, so what we have to do first is find the acceleration vector, and so let's take the derivative of the velocity vector. If we do that, a of t will be equal to the derivative of a negative sine t, and the derivative of sine is cosine, so we get negative cosine t I, and then the derivative of cosine t is the negative sine t, so we have minus sine t j, but then the derivative of 2 is 0, so there is no z component. This is the acceleration vector. Now let's evaluate it at pi divided by 3, so we'll have a of pi divided by 3 is equal to negative cosine of pi divided by 3. Cosine of pi divided by 3 is 1/2, so we get negative 1/2 I, and then sine of pi divided by 3 is the square root of 3 divided by 2, so we have minus the square root of 3 divided by 2, j. All right, so now we have the acceleration vector at pi divided by 3 and the unit tangent vector at pi divided by 3, so now we can take the dot product of those two vectors to find a tangential component of acceleration. So let's do that next. I moved our acceleration vectors over here, but now what we're going to work on is a sub t at pi divided by 3, that's going to be equal to a of pi divided by 3 dot t of pi divided by 3. And so if we perform that dot product, we're going to take the sum of the product of corresponding components. And notice that there is a scalar multiple for the unit tangent vector. We can just pull that to the outside of the dot product. So we can ignore it when we're multiplying our components, but just remember to multiply everything by 1 divided by the square root of 5. Okay, but then for the dot product, we'll have negative 1/2 times the negative square root of 3 divided by 2. So we have negative 1/2 times the negative square root of 3 divided by 2 plus the product of the y components, negative square root of 3 divided by 2 times 1/2. So we have the negative square root of 3 divided by 2 times 1/2. And then for the z components, there is none for the acceleration vector, so it's 0 times 2, which is 0. So we have plus 0. All right, now simplifying, those two negatives would cancel out, so we'll have the square root of 3 divided by 4, because 2 times 2 is 4. So this is equal to 1 divided by the square root of 5 times the square root of 3 divided by 4 plus the negative square root of 3 times 1. We'll have a numerator of the negative square root of 3, and then 2 times 2 is 4. So really what we have here is the square root of 3 divided by 4 minus itself, right? That 0 is not going to do anything. So this is all we have, and a number minus itself is 0. So what we find here is that the tangential component of acceleration at pi divided by 3 is 0. There is no tangential acceleration for this position vector at that time, which does mean that all of it is going to be in the direction of the unit normal vector. And so the magnitude of the acceleration vector will actually be the value of the normal component of acceleration. But just to show you that that's true, I'm going to use this formula right here to find the normal component of acceleration. In order to find it, we need to take the square root of the magnitude of the acceleration vector squared minus a sub t squared. We already know it's 0, so we're just going to be taking the square root of the magnitude of the acceleration vector squared, which will just be the magnitude of the acceleration vector. Okay, so let's quickly find the magnitude of the acceleration vector here. Specifically at t equals pi divided by 3, the magnitude of a of pi divided by 3 is equal to the square root of negative 1/2 squared, that will give you 1/4, plus negative the square root of 3 divided by 2 squared. The square root of 3 squared is 3, 2 squared is 4, so we have plus 3/4. 1/4 plus 3/4 is 1, so the magnitude is equal to the square root of 1, which is equal to 1. So for the normal component of acceleration, we get that it's equal to the square root of 1 squared minus 0 squared, right? The magnitude of the acceleration squared, so we have 1 squared minus a sub t squared, which is 0. So we have 0 squared. 1 squared is 1, 0 squared is 0, 1 minus 0 is 1, the square root of 1 is 1. So we find that a sub n is equal to 1. That is the normal component of acceleration. And so now we have both the tangential and normal components of acceleration, as well as the unit tangent vector. Now all we are missing is the unit normal vector. And that's how we're going to end this problem. We want to solve for that unit normal vector. We can find that unit normal vector by making use of this formula right here. We know everything in this formula except for the unit normal vector. So let's set this up and solve for it. If we set up this equation, we want to start with the acceleration vector. And remember, we are working at that value of t, pi divided by 3. So we're going to take this acceleration vector and set it equal to all of this. So we have negative 1/2 I minus the square root of 3 divided by 2 j. And that will be equal to a sub t, which is 0 multiplied by the unit tangent vector. So I'm not going to bother to write out the unit tangent vector. Since a sub t is 0, you have 0 times t of pi divided by 3. That's just going to be 0. So there's no reason to write all of those components out and then just multiply it by 0. That term is 0, and so we're just going to be adding that to a sub n, which is 1. So I'll write 1 times the unit normal vector at pi divided by 3. And really, we're done. We already have the unit normal vector at pi divided by 3 because this vector times 1 is just the same vector. This is 0, and so the unit normal is just equal to these two terms. It's equal to the acceleration vector at pi divided by 3. So we find that n of pi divided by 3, or the unit normal at pi divided by 3, is equal to negative 1/2 I minus the square root of 3 divided by 2 j. That is our final answer for the unit normal vector, and also the last thing we needed to find for this example. Okay, so hopefully now you can see why I chose to use this formula. Finding the unit normal vector this way is probably a little bit quicker and easier than if we were to try to find it the normal way, by finding the unit tangent in terms of t, taking its derivative and dividing it by its magnitude. We don't really want to do that here. Because of how these four values are related, in this equation, we can sort of skip that work and just find the unit normal this way instead. Okay, now granted it was a little bit easier here than it might be in some cases because a sub t was 0, but even so, if we had an actual vector here, you would just subtract those components over to the other side, and then you would have solved for the unit normal vector anyway. Okay, but that's it for this example, and so let's practice doing this whole process one more time with the final example for this video. Okay, so here's our final example. We want to find the unit tangent vector, the unit normal vector, as well as the tangential and normal components of acceleration at t equals 1 for the given space curve. And this time our space curve r of t is equal to ti plus t squared j plus t squared divided by 2k. Alright, so this is the exact same type of problem we did in the previous example, except now we have a different position vector and a different value of t that we want to work with. Okay, so we're going to use the same exact process and the same formulas as last time. We're going to make use of this definition of the acceleration vector using the tangential and normal components, and we will make use of these two formulas down here, that a sub t is equal to the dot product between the acceleration vector and unit tangent vector, and then this formula down here, which is based on the Pythagorean theorem that allows us to easily find a sub n, or the normal component. Okay, I sort of handpicked these two because I find them to be the easiest to work with in these types of problems where you also want to find the unit tangent and unit normal vectors. Of course, there are other ways to find these components, so if you want to use a different formula, that's fine, but this is the way I recommend going about it in this type of problem. But to get started here, I want to begin by finding the unit tangent vector at t equals 1. Remember, we don't have to find anything in terms of t here. We want to find these four things at a specific value of t equals 1. And so let's find the unit tangent vector at t equals 1. To start, we need to find the velocity vector, or the derivative of the position vector. So v of t is equal to the derivative of these components. The derivative of t is 1, the derivative of t squared is 2t, and then the derivative of t squared divided by 2 will just be t, because 2 multiplied down will cancel out with this 2, and then subtracting 1 from the exponent just leaves you with an exponent of 1. So we get 1i plus 2tj plus tk. All right, and then we will need the acceleration vector later, so I'm just going to go ahead and find that right now. The acceleration vector a of t is equal to the derivative of these components. The derivative of 1 is 0, so there is no x component. But the derivative of 2t is 2, and the derivative of t is 1, so we get 2j plus 1k. All right, so that takes care of that. We don't need to do that later. But what we do need to do is evaluate both of these vectors at t equals 1. We'll need the velocity vector at t equals 1, and then its magnitude to find the unit tangent vector, right? In this case, the unit tangent vector at t equals 1 would be equal to the velocity vector at time 1 divided by its magnitude. Okay, because that would be the same as r prime divided by its magnitude, which is how we found the unit tangent in the past. Really, we're doing the same calculation here. We're just calling the first derivative the velocity vector. All right, but let's find the velocity and also the acceleration at time 1, because we will need a of 1 later on. Starting with the velocity, v of 1 will be equal to 1i plus 2 times 1j. 2 times 1 is 2, so we just get 2j, and then plus 1 times k, which is just k. Then for the acceleration at time 1, notice that there's no values of t here. It's just 2j and k. So it's going to be the same exact vector. In fact, instead of writing it down here, I'll just do this. I'll write it right here. A of 1 is equal to 2j plus k. All right, now let's find the magnitude of v of 1. We're going to take the magnitude of the velocity vector at time 1. So we'll have the square root of the sum of these components squared. We'll have 1 squared plus 2 squared plus 1 squared, which means we have 1 plus 4 plus 1, which will be the square root of 6. And so I'll just erase this and write the square root of 6. Okay, so now let's set up our unit tangent vector at t equals 1. We're going to take v of 1 and divide it by its magnitude. So we'll just have 1 divided by the square root of 6 times this vector. All right, the unit tangent vector at t equals 1 is 1 divided by the square root of 6. That's 1 divided by the magnitude of v of 1 times v of 1. So we have I plus 2j plus k. And that right there is t of 1. Now let's move on to the next thing we want to find. We're going to save the unit normal vector for last again. Let's move on to the tangential component of acceleration. That will be the dot product between a of t and t of t, which at t equals 1 means we're going to take the dot product of the acceleration at time 1 and the unit tangent at time 1, which is these two vectors right here. So let's do that. A sub t will be equal to a of 1 dot t of 1. And so if we calculate this, we want to multiply the corresponding components between the two vectors, but don't forget that we have this scalar multiple on the outside of the unit tangent vector. We don't have to worry about multiplying that by each of these components before doing the dot product. We can just multiply that scalar by the result of the dot product. All right, so we'll have a sub t is equal to 1 divided by the square root of 6 times the sum of the product of corresponding components. But now we can ignore that 1 divided by the square root of 6. So multiplying the x components, there is no x component for the acceleration vector at time 1. It's just 0. So you'd have 0 times 1, which is 0. So we have 0 plus the product of the y components. So we have 2 times 2, which is 4. And then we'll add that to the product of the z components. So we'll have 1 times 1, which is 1. So we have 4 plus 1. That's 5. And so 5 multiplied into the numerator gives us a sub t is equal to 5 divided by the square root of 6. That is the tangential component of acceleration in this example. So now we have both the unit tangent vector and the tangential component. Now let's find the normal component of acceleration, and then we'll find the unit normal vector. To find the normal component, I'm going to use this formula, which requires that we know the magnitude of the acceleration vector. Specifically, we will want that at t equals 1. So let's take the magnitude of the acceleration vector here. The magnitude of a of 1 will be equal to the square root of the sum of these components squared. So we'd have the square root of 2 squared plus 1 squared. That would be 4 plus 1, which is 5. So the magnitude is the square root of 5. Okay, so now let's set up this calculation here. The normal component of acceleration will be equal to the square root of the magnitude of the acceleration vector squared, specifically at t equals 1. So we're going to take the square root of 5 and square it. So we have the square root of 5 squared. And then we are subtracting the tangential component of acceleration. So you want to square 5 divided by the square root of 6. So we have 5 divided by the square root of 6 squared. And now simplifying, the square root of 5 squared is just 5. So this is going to be equal to 5 minus 5 squared divided by the square root of 6 squared. 5 squared is 25. So we have 25 divided by the square root of 6 squared, which will just be 6. All right, now in order to simplify this, we want to write 5 in terms of sixths, and 5 would be the same as 30 divided by 6. So let's write that like this. We would have 30 divided by 6, that is 5. And so now that we have a common denominator, 30 minus 25 is 5. So we get the square root of 5 divided by 6. And so if you wanted to, you could keep it in that form, but you might prefer in this case to actually rationalize it. Here's what I mean by that. You could rewrite a sub n to be the square root of 5 divided by the square root of 6, and then multiply by a form of 1 of the square root of 6 divided by itself. That way the denominator will just be 6. There will be no radical or no square root. And then 5 times 6 is 30. So what this becomes is the square root of 30 divided by 6. That is the normal component of acceleration at t equals 1 for this position vector. Okay, that's what the square root of 5, 6 reduces to or simplifies to if you rationalize it. Now, we only have one thing left to find, and that is the unit normal vector, which we will find using this equation right here. We know everything else. We have the acceleration at time 1, the unit tangent vector at time 1, and the tangential and normal components of acceleration at time 1. So we can solve for the unit normal vector. And so let's do that. Starting with the acceleration vector, we want to use a of 1, which is right here. So we'll have 2j plus k is equal to a sub t, which is 5 divided by the square root of 6, which, by the way, if you want to rationalize that as well, you can multiply the numerator and denominator by the square root of 6. So that would look like this. You would have 5 square roots of 6 divided by 6. It's up to you if you want to do that or not. I'm not going to do that in this case. I'm just going to write it the way we had it, which is 5 divided by the square root of 6. But then you want to multiply that by the unit tangent vector, which is this right here. So we're going to be multiplying by 1 divided by the square root of 6, and then we're multiplying by I plus 2j plus k. And then we have plus a sub n, the normal component of acceleration. So we have the square root of 30 divided by 6 times the unit normal vector at t equals 1, right? That's what we're trying to find here. Everything else in this equation was in terms of t equals 1, so will the unit normal vector in this equation. So that's what we want to solve for. And to do that, we need to simplify everything else and then combine our like terms. Or really, since we're working with vectors, we want to combine the like components or add them together. Starting right here, 5 times 1 is 5. The square root of 6 times the square root of 6 is 6. So we get 2j plus k equals 5/6 times that vector of I plus 2j plus k, and then plus the square root of 30 divided by 6 times the unit normal vector at t equals 1. All right, then to make things easier for ourselves here, notice that both of these two terms have a common denominator of 6, or they're both being multiplied by 1/6. So if we multiply both sides of the equation by 6, that will be gone. So doing that will give us 12j plus 6k, because we have to multiply this side of the equation by 6 as well. And then that will be equal to 5 multiplied by this vector. So we'd have 5i plus 10j plus 5k, and then plus the square root of 30 times the unit normal vector at time 1. All right, then let's move these three terms over to the other side of the equation. There is no I component over here, so we will just have negative 5i. All right, we'll have negative 5i, and then subtracting 10j from both sides, we'll have 12j minus 10j. So that gives you positive 2j, and then subtracting 5k from both sides, 6k minus 5k is 1k, so we have plus k, and that will equal the square root of 30 times the unit normal vector at time 1. Now finally, to solve for the unit normal vector, we just have to divide both sides by the square root of 30. So what we get is that the unit normal vector at time 1 is equal to 1 divided by the square root of 30 times negative 5i plus 2j plus k. And there we have it. That is the unit normal vector in this scenario at time equals 1. All right, and so that's it for this example. We found all 4 things we wanted to find, and so we're done. That is it for this example, and this was also the last example for this video. But if you want to work more with the tangential and normal components of acceleration, I do have some bonus videos on this topic available on my membership site. So if that's something that interests you, feel free to consider becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.